My name is Brian Catanzaro. I'm really excited to be here and talk about some of the work that we've been doing at Baidu to use high-performance computing to make AI better. And I actually wanted to sort of, as my question, my motivating question, why is HPC so important to AI? I wanted to explain that to you because I think that it's kind of an ongoing trend, and I think we're just at the beginning of the importance of HPC to artificial intelligence. So let's get started. When I think about how we make progress in AI research, I think about this cycle that we go through from idea to code to experiment and then back to idea. So basically, when we want to figure out how to make a new model, solve a new problem with AI, somebody starts out with an idea, and through some math or some other process, they figure out what kind of model they want to make. They need to encode that into a binary that can actually run on a computer that will train the model on a training set. So we have a training set, we've got a program, we run it, and once we do that, we can test it and see how we did, and that usually generates new ideas. Maybe we need to improve our data set, maybe we need to make the model a little bit different. So we get new ideas from that, and we go around and around this circle. So what does this mean? It means that progress in AI is really gated by the latency that it takes for us to generate new ideas, to go around this circle. And so that means that we care about the time that it takes for each one of these three steps. And in particular with deep learning, we have lots of new opportunities. We're able to solve problems that previously we just didn't know how to solve. But at the same time, it brings challenges because, especially with training these big neural networks, it takes a lot of time. And so that testing step, once we've got some code and we need to actually run it, it can take quite a bit of time. For example, we were talking about this at lunch. I guess when people were doing neural networks back in the 80s, they used to train their models for a year or longer. And things have gotten progressively shorter. So nowadays, when we train one of our models, if it takes longer than a day or two, then we're really impatient. We want to see results immediately. As the faster we can go around that loop, the more progress we can make. Uh-oh, Auni, I'm going to need your password. Okay, I'm going to wiggle the mouse a lot to make sure this doesn't happen yet. All right, I really love this quote from Geoff Hinton, who is one of the pioneers in deep learning. Back in 2012, he said, referring to the rapid deep learning advances made possible by greater computing power and especially the rise of graphics processors, Geoff Hinton added, "The point about this approach is that it scales beautifully. Basically, you just need to keep making it bigger and faster, and it will get better. There's no looking back now." That was 3 years ago, and we're still not looking back. Basically at about the same time that he was saying that, there was a result that came out of a team led by Kwok Le, scaling unsupervised learning to, at the time, something really huge, like a inconceivably large neural network. And it got a lot of press because it was able to find images of cats in YouTube videos without ever being taught what a cat was. You guys have probably heard about this before. So the interesting thing from a systems point of view is that to obtain this result, they trained their model on 1,000 machines for a week. So that was 16,000 cores running for a week. And a group of us were thinking, I bet if we applied standard high-performance computing techniques, we could reduce that latency quite a bit and use far less hardware. And so a team led by Adam Coates, who's now the director of the AI lab here at Baidu, was able to reproduce that result using 300 times fewer nodes. So we were using 3 nodes instead of 1,000 running for a week. So we're using a bunch of GPUs using MPI, which is a standard HPC library for coordinating multiple processes, and using high-performance interconnect like InfiniBand. So that was pretty exciting, and I think for a lot of us, that was when we started to understand that high-performance computing was really going to be the future of AI, because it took something that previously required, huge computing resources like, getting access to 1,000 nodes in order to run an experiment, to something that, pretty much any researcher could have access to 3 nodes is within the reach of most budgets at academic labs, for example. And so that was really exciting. Okay, so now a few of us are believing like HPC is really important. Well, what is HPC? I wanted to define that a little bit. And I wanted to contrast it against cloud computing. So for my icon here for HPC, I've got big iron, an anvil. And for cloud, we've got a lovely cloud. I think most AI research in the past has been oriented towards cloud computing. And so it is a different kind of mindset when you're doing HPC. So what do I mean by that? First of all, with HPC, we focus really intensely on what is the limit of the hardware, the fundamental limit of how fast we can make this go. So we call that the speed of light, and we reference everything to that speed of light. So when we're thinking about how long does something take, we hardly ever say, oh, it went 10x faster today than it went yesterday. We instead say, well, we went from 1% of the speed of light to 10% of the speed of light, right? And those are fundamentally different points of view because when you're oriented towards the fundamental speed of light of the hardware, then you're going to make decisions in a different way. There's a mindset that goes along with HPC. Another thing that's common with HPC workloads is that they are limited by floating point operations, or basically math, or memory bandwidth. So how quickly can we move data around, whether it's on and off the chip or between processors in a system with multiple processors. And generally not bound by I/O. So not bound by, for example, trawling through petabytes of information. Also, HPC applications are monolithic. So when we write them, the software that we use is very tightly coupled. And that allows us to scale much more efficiently. Basically, we get better scaling because there's not a lot of abstraction. It's really close to the metal. So in contrast, cloud computing that a lot of people have used, like for example, if you used Hadoop, or if you've used Spark to train models, these are traditional cloud computing models where you are focused mostly on programmer productivity. So you want to develop as fast as possible, and there's this underlying assumption that hardware is almost free. Like the cloud is big, it just gets bigger. You can just keep scaling in the cloud, and that works for many applications, especially for applications that are I/O bound. So, for example, if we need to count all the instances of the name Brian on the internet, that is a very I/O bound problem, and it works really well. It scales beautifully with a cloud-based approach. However, training deep neural networks is not like that, and I'm going to explain why that's the case in a second. The other thing about cloud computing is that it's confederated, so people write applications built on communicating services. It's designed to be resilient, so if some of the servers go down, it's okay. You can continue right on, and it's composable, so you usually build up things out of a lot of smaller pieces, and they sort of communicate loosely. So that's kind of the cloud mindset. The HPC mindset is really different. It's more of a traditional supercomputer mindset. So I'm going to explain to you why that makes sense for AI. So the process of training deep neural networks is dominated by math. So on the left here, I have a very simple equation for the output of a neuron. It's basically just you do a dot product of a weight vector and an input activation vector, and you produce one output after you pass it through a nonlinearity function. So probably many of you have seen this before. When you gang up neurons, so that instead of just computing the output of one neuron, but you have the output of many neurons, you have the situation on the right where you have an input vector x and an input vector y, and then you have a weights matrix w that kind of matches between all the inputs x and all the inputs y. And so when you're computing with multiple inputs and multiple outputs, especially when you're computing with multiple examples at the same time, then that computation turns into a matrix multiply. So in HPC land, we call that GEM. That comes from the basic linear algebra subroutine that implements matrix multiply. And every vendor, like whether it's a GPU or a CPU or any other kind of device, will give you a super optimized implementation of this primitive, right? Matrix multiply is really fundamental. So what's nice about matrix multiply from a systems point of view is that it's compute limited in general. So if you look at the amount of work that you have to do to perform a matrix multiply, it's sort of this third order polynomial, m times n times k, whereas the amount of data movement is second order. So if you're just looking at the input movement, it's just two second order terms. So basically what this means that if you look at it as we scale it, then the amount of work gets bigger much faster than the amount of communication, and so it's compute bound. And convolutional layers that are often used in other kinds of neural networks are even more compute bound than these simple fully connected layers that I've diagrammed here. Okay, so we've made this observation that training deep neural networks, almost all of the work is going to be found in these very compute dense kernels. So what does that mean? Well, let's look a little bit more at the computational characteristics. If we look at how many arithmetic operations we perform while training a neural network, and then divide that by how many bytes of data that we have to transfer to move our training set through the machine, then it's about exaflops of work. So an exaflop is like 10 to the 18, so it's like a billion floating point operations. So we do multiple exaflops in order to train a model that uses terabytes of data. So if we take that ratio, then we get about 10 to the 6, which means we're doing about 1 million floating point operations for every byte of data that we transfer. So that is really computationally intense, and that is what drives this difference towards the reason why HPC makes sense. In contrast, many MapReduce style jobs, so if you're doing Hadoop, for example, you may be trawling through petabytes of data, but for each piece of data that you touch, you may be doing order 1 operation, like sum up all the times that Brian occurs on the internet, like I mentioned before. You know, basically I'm going to look at every word, and if it's Brian, then I increment something, and if not, then I just pass through. So there's really not a lot of compute happening there. And if we took the ratio there, it would be about 1. And so that would point to this being a much more I/O-bound problem. And then because our data sets, although they're large from a neural network point of view, they're not actually that large in the sense that they can fit easily on a hard drive. And so we don't need like distributed file systems and fault tolerance and a lot of the resilience that come along with cloud infrastructure. We can go with something simpler. So that's what we do. As I mentioned before, the turnaround time is key. So we want to go from idea to code to test back to idea as fast as we can. We want to use the most efficient hardware. So we go with parallel computing. We use heterogeneous computing. And specifically, we use GPUs. And we care a lot about fast interconnect. So we try to make all of our communication happen over PCI Express or over InfiniBand because those are much faster than Ethernet. We also push strong scalability so that our we can get results even faster by using more hardware. And all of this that I'm saying right now is just standard HPC. So I put a picture of the Titan supercomputer here. You know, people have been doing HPC for a long time, and there's established ways of thinking about these problems that can help you solve them. So that's what we do, is we apply that to AI. Okay, so what do I mean by heterogeneous computing? We have a latency optimized CPU and a throughput optimized GPU that work together to solve a problem. And in this picture, I've actually got die photos of a big CPU with 15 cores compared with a GPU that also has 15 clusters in it. And I always find looking at these diagrams interesting. The CPU, if you can see those rainbow areas, those are the cores, and the green areas are the caches associated with them. So they're spending a lot of die on caches in order to reduce the latency of operations. Whereas when you look at the GPU, each one of those green clusters is just filled with math units. So it's just like really dense. It's like a chip that's made out of math units. So when you have when you have a workload like training deep neural networks that's very math intense, it makes sense to go with something heterogeneous. It saves a lot of power. And then because we save power, we can actually get more work done. I'm going to skip this slide because I'm running out of time. Okay, so I want to talk about strong versus weak scaling. So this is a traditional HPC concept. Basically, there's two ways that you can use more hardware. The first is you which we call strong scaling, is you keep the problem size the same and you try to use more hardware for the exact same problem. And that allows you to solve today's problems faster. However, it's usually more challenging because as you subdivide the problem, each subdivision is going to be smaller, and everything gets less efficient as you make the work smaller. There's more communication, and the processors themselves get less efficient. So an alternative is weak scaling, which is you scale the problem size with your number of processors as you grow the machine. And that allows you to solve bigger problems, but doesn't really help with today's problems. So with AI, we focus on strong scaling because, as I said, we're trying to reduce the latency that it takes to go from idea to idea. I'm going to skip this as well. Okay, so what kind of infrastructure do we have here in the Silicon Valley AI Lab? We use CUDA GPUs. Specifically, we use a lot of Titan X GPUs because they're really great at single precision arithmetic. We stick them in boxes that have 8 of them in one box, so it's very dense. This allows us to keep most of the communication on PCI Express, which is really fast. And then to go between boxes, we use Mellanox interconnect. So what does it look like inside of a node? Basically, each one of our nodes has 2 sockets and has a CPU in each of those sockets and is connected to a tree of PCI Express switches. And what this allows us to do is have, of all of our 8 GPUs, each pair of GPUs that sit next to each other can communicate at full speed to each other simultaneously with all the other pairs of GPUs. So the bandwidth that we get and the latency of interchanging data between neighboring GPUs is really, really small. And then it also allows us to group 4 GPUs together into a peer-to-peer domain so that we can, again, move data more efficiently between them. We avoid, as much as possible, moving data across the link between the 2 CPUs in that socket because that link is much slower than PCI Express. So anyway, I'm giving you all these details just to give you a sense of some of the things that we worry about when we're mapping the process of training a neural network onto hardware. We care about the details because it really matters, and we get a lot of scalability out of that. So how do we deal with parallelism? In general, when you're mapping neural networks onto hardware to train them, there's 2 fundamental ways of getting parallelism. One is called model parallelism, where you take the model and chop it up into pieces and then have the pieces communicate as you're propagating information through the network. And the second is data parallel, where you observe that, hey, my training set's huge. I can chop up my training set into smaller pieces and then give each piece of the training set to a different processor. And then each processor is going to learn something from that. We get a gradient that we're going to use to update the weights. We use an all-reduce, which basically gathers update the gradient from each processor and brings it all together and then broadcasts the result back out to all the other processors. So in HPC land, we call this an all-reduce. And so we use both of those techniques. For model parallelism, we have a distributed array. Basically, what this allows us to do, of all those matrix math that we were talking about earlier, we can subdivide them into smaller pieces, map them onto different processors, and then compute in parallel. So this reduces the amount of memory that we need to use per GPU, which is important. But scaling this is difficult because it's very latency sensitive. So so it's a fun challenge for us as we try to make this scale. And then, of course, this can be composed with other kinds of parallelism, like data parallelism, for example. So that's what we do. And I wanted to show you this performance graph. So basically what this is weak and strong scaling for training one of our recurrent neural network models on 4, 8, and 16 GPUs. And what the y-axis is throughput per GPU. So if you think of like how efficiently each GPU is running, if we got perfect scaling, everything would sit there at 1, right? Because it would basically say as we added more processors, all of them worked at the same speed. Unfortunately, that's hardly ever the case. So as we try to strong scale from 4 to 8 GPUs, we give up a certain amount of performance. That's the difference between the points on the left in blue and in red. And as we go to 16, obviously it gets even worse. So if we want to use 16 GPUs, we need to go work on a bigger problem. So the x-axis here is the mini batch size, so we can increase the number of examples that we're pushing through the network at each phase of the training, so that we can increase the amount of work and get better scalability. Yeah.
Have you tried smaller mini batch sizes? And can you talk about that?
Yeah. So we definitely have. So the question is, have we tried smaller mini batch sizes? The choice of mini batch size has a big impact on how efficiently the GPU is going to run, because if you give, basically that mini batch size controls the arithmetic intensity. So if the mini batch is 1, a lot of things that were compute bound become bandwidth bound, and because you just don't get as much reuse of the weights. So we tend to work with mini batches that are fairly large, because that keeps everything happy computationally. And there's a trade-off, right? So if you make mini batches smaller, you typically require fewer iterations of your solver in order to converge. But if the cost of each one of those data examples that you put through that smaller mini batch is increased greatly, then it might not make sense. So we pick the mini batch size based on whatever is the fastest time to solution for us, where solution is defined in terms of convergence. Great. So with all this work that we've done in order to optimize our hardware and our software and use HPC techniques to sort of inform how we optimize it, we're able to get some great results. On a single GPU, we can sustain 60 to 65% of GPU FMA peak, which is really great. So that's our speed of light, is how many floating point operations per second can the chip do. And it's a really big number because the chip is just filled with them, right? It's just basically a big array of floating point units. So the fact that we're able to keep them all busy at 60 to 65% of the speed of light is a great accomplishment. But I'm even more proud of the fact that when we use multiple GPUs together, so for example, when we use 8 GPUs, we're able to sustain about 50% of peak, which means that we're able to sustain about 26 teraflops on a single node. So that's pretty exciting, and it's only thanks to the work of a team of people, of really great HPC experts here at Baidu, who have spent a lot of time deeply looking into all of the issues that happen when you map one of these applications onto the hardware. Okay, so in conclusion, I hope I've been able to convince you that training deep neural networks is an HPC problem, and using HPC techniques can make a really big difference in the kinds of problems that you can tackle. It reduces training time. This lets us scale to larger models and larger data sets, and ultimately leads to progress in AI and lets us solve problems that we couldn't solve before. So that's it. Thanks.